All right, thank you. So last talk of the day, my voice is so far so good, so we'll see how that goes. Thank you for inviting me here, Shannon and Dylan. I'm glad to be back. So title of talk today, In Situ Solar Machine Networks for Satellite Calibration Validation. I'm going to emphasize in situ networks in this talk. Calibration and validation is a completely different talk. Probably take a couple of days to go over that. So, but in the context of today's session, I think this is a very good time to talk about calibration and validation. Most of the talks today talked about instrumentations that look down on Earth to collect data and do some geophysical processing and estimation. Now is a good opportunity to see, okay, is the satellite or the CubeSat seeing what it's supposed to be seeing, and how do we go about providing data to help? The title of our project is Sourcescape. It's been run by Mahta at USC and Dara at MIT a couple of years. I want to point out some of our key collaborators. Agnello Silva is at Meter Group. He's kind of the brains behind a lot of our technology development. And then Richard and Kazem at USC have been helping him out last couple of years. The talk is broken down to three simple parts. One, I just want to motivate the need for in-situ networks in the context of SMAP and solar moisture estimation. Then we're going to move into our Sourcescape project, kind of explain the technology and the data delivery and data collection. Then I have some very simple example highlights of how we use the data and how you could use the data for your research. Just a quick show of hands, how many people have heard of SMAP? How many people have used SMAP data? Okay, that's good. So, that's really short. So just a very short overview. SMAP, I think Andrew earlier on talked about that too, is an L-band scanning radiometer. At the moment, it's a radiometer. It started off with a radar as well, both at L-band. Unfortunately, the radar failed after about 2.5 months. Quite unfortunate. But if you are interested in using radar data on a global scale, it's excellent quality. I've used it in my PhD myself, so I wouldn't dismiss the short period as an efficiency. I highly encourage, if you're interested in actually download and use that data from the, you can get it from the Alaska satellite facility. The goal of SMAP essentially is to go around the world, measure surface soil moisture. I'm talking about surface soil moisture about 10 to 5 centimeters in the top level. Knowing soil moisture has profound implications in the water, energy, and carbon cycle of the Earth. Chris earlier on talked about the latent energy of the ocean. The same concept also applies to land as the moisture evaporates. How much moisture, how much energy is required, link the water and energy budget to each other. So knowing soil moisture globally and frequently is very important. Once you know that, you can also feed that into different science applications, and that can affect day-to-day life. This is one of the SMAP approved charts, and part of the mission is to get soil moisture, then improve the flood predictions and drought predictions using both the radar and the radiometer. This is a little animation of SMAP going around the world. So you have your it's about a 6-meter dish mesh antenna. Rotates, I think, about 14 RPM with a corrugated horn antenna. As you see the helical scanning on the Earth, goes around. So at some point, we should start seeing some data showing up. It's actually over Michigan, so whoever designed it is Michigan. So this is a kind of a schematic of what the radar SAR is. There's a kind of nadar gap in between where they can't do exact processing. This is what a radiometer image will look like, and then you translate that into soil moisture. So blue is very moist, orange will be very dry. As the satellite goes around the Earth, you get almost a 3-day coverage of the surface soil moisture. So let's make this finished, and I can go to the next slide. So you can see like the western US is very dry, very wet on the eastern side. You can see the dark blue, moist Amazon. That's a kind of SMAP in a nutshell. Okay, so the next critical question is, once you go through the radiometer processing and soil moisture estimation, how do you make sure what the satellite is saying is correct? Before you actually get to that point, there's two things you need to consider. One is soil moisture by itself is highly variable across the landscape. At different scales, from meter, 10 meter, 100 meters to kilometers, soil moisture variability is influenced by a whole different range of processes. And this nice little schematic here kind of highlights some of that. You know, at the scale within our, like the city area or even your garden area, soil moisture is influenced by topography. You go to larger scales, it's the landscape and vegetation variation. And if you go larger and larger scales, regional scales, it's the weather patterns and precipitation patterns that influence soil moisture. On the other hand, you have down-looking satellites at different frequencies and different ground resolutions, and what they do, they kind of average and mask all of that variability into a single pixel. I put some examples here from the SMAP 3 kilometer radar and brightness temperature. If you look carefully, zoom in, there's a lot of details both in the radar SAR measurement and the soil moisture, derived soil moisture, but because of the large antenna footprint from the radiometer, a lot of that is masked and averaged into that process. So the question for validation is, how do I link the knowledge and concept of soil moisture variability in a landscape with the resolution that our satellite sees? Any ideas, any proposals? How are we going to validate? Okay, it's quite simple. You need a lot of sensors in the ground. And the key word here is representativeness. It's because of this variability, you need to have some knowledge and some idea of where exactly to put the sensors in the ground, that when you average up or do whatever algorithm to collect all the data from that to the satellite footprint is representative of what's going on the ground. This by itself is a whole different topic of discussion, whole different science exactly. I don't have much time to go through that here. Simplest way is just average up. Other ways you can do arithmetic, weighted average, or a whole bunch of other ways. You can probably get a bunch of PhDs out of just this upscaling technique. So what do you mean by soil moisture variability? Let's look at some real data from some of our sites at different scales. So this is a sensor location that we have in our site, Tonzi Ranch, California. It's an hour east of Sacramento. These little red markers here are actual sensors in the ground. 1 year of 20-minute soil moisture information. If you haven't seen the soil moisture time series, it's a jump decay process. Every time it goes up, it's because the rain is coming down. And once the rain passes, it just decays, but at variable rates. If you look closely, some of these lines, for example, the purple line here, soil moisture drains down much faster, some of these a bit slow. There's a ripple on top of that, that's not noise, that's like a diurnal cycle of soil moisture. The temperature influence as the temperature of the air and the soil change throughout the day, there's some variation of soil moisture. But the key takeaway here is even within like a 200-meter radius, point by point, there's some slight variability in soil moisture by itself. So that's at a very small scale. Let's go to a larger scale. In another location in Arizona, two single soil moisture sensors about 10 kilometers apart. The general trend of the sensors are the same, jump, decay, but what you see here, this blue line in Kendall over here has 2 rain events that were not shown up here. And that's because of local precipitation, that's because weather events are affecting the process. So if you have your satellite aircraft over passing, it's going to kind of average all of this information. What is localized precipitation? This is a picture I took from this location. I'm standing about a couple of kilometers away from me. There's this huge downpour of rain. It's about August 2015. There's a monsoon season there, so that's when those events happening at that time. Okay, so this is kind of setting the stage of understanding soil moisture variability and knowing satellite soil moisture estimation has different resolutions. Goes into our project called Sourcescape. Project title: Soil Moisture Sensing Controller and Optimal Estimator. In the NASA language, TRL7. What exactly is Sourcescape? It's basically a clusters of wireless sensor networks with the goal of measuring and reporting soil moisture information in near real time, both from the surface and the root zone, so we get sensors at different levels in the ground, and then feeding that to different earth science missions, SMAP, Air Moss, and recently we participated in Cygnus, to give that data so they can validate the soil moisture products. Another goal that we had early on is, okay, how do we advance the wireless sensing technology, especially from a low power perspective, and take that technology forward. So it's going to be a two-sided goal here. The way we've done this is we have our own custom-built hardware. It started at Michigan. We completed and improved it in USC. Still doing some revisions and updates, and also some very basic wireless sensing communication network protocols that we have. A typical network a wireless sensor network that gives you soil moisture may look something like this. This is the location we have in Millbrook, New York. These red, purple circles, these are what we call our wireless end devices. These are custom-made electronics housed in these PVC enclosures. At the end of these, we dig a hole and put soil moisture sensors at different depths. Each of these wireless end devices communicate with this central location, which is a local coordinator. It has two roles. One is to talk to the end devices, get the data, and then shift all of that to the data server and the end user. So this is a very high level of network architecture to see. One thing I want to point out here that the end devices, these are all battery powered. So we don't use rechargeable batteries on the end devices, but the solar panel, the local coordinator, because it's a little bit more computation heavy and does a bit more heavy lifting, there's a solar panel. Data is available at the project website, sourcescape.usc.edu, or at the Orno DAC, Oak Ridge National Lab, so it's free to download and use. I have a table at the end with all our sites.
Quick question. How long do the batteries last?
Okay, I'll go to it. Averaging around 1.8 to 2 years. Yes. So soil moisture by itself is a very slow-moving process. Unless there's a big rain event, it varies very slowly. So you don't need a very fast sampling process. Right now we have our setup between 20 to 30 minutes, depending where we are. It's overkill. You can go to 1 hour. That extends the lifetime. The way the system works is most of the time the end devices are in sleep mode, and they're only active when they need to make a measurement, transmit that, and then they go back to sleep. And there's some power matching techniques and power gating techniques to preserve all of that. We can go towards using solar panels to operate and charge the batteries, but that's something we can consider in the future. Another thing I should point out here is that in terms of wireless communication, wireless networking, there's no message relay or message hops. That means that if this sensor is collecting data, it only attempts to transmit the data to local coordinator. The messages aren't routed around, and that kind of helps us with energy efficiency, because transmitting the information has the highest power consumption by itself. Okay. So what does this mean in practice? You have a little sensor network, you put sensors around. What does that mean in terms of calibration, validation efforts? Traditionally, you have 1 or 2 sensors in large areas, considered sparse. Once you go to wireless sensor approach, you go from sparse to the technical term is semi-sparse. And you get more samples, you get more representativeness. That's what the essential idea is. Locally, you can have more and more measurements to capture the variability of soil moisture. And when you average up or you upscale, it's more representative of what the satellite can do. That's the essential implication of a wireless sensor approach. Some of the components that we have, the design, this is a local coordinator. I call it the brains of the system. This custom-made electronics here. I have 2 microcontrollers up here. One of them is responsible for all the wireless communication stuff. The other one, we call it the scheduling controller. It controls all the different components of the local controller. You have to kind of task management on top. Here is the socket where we have the off-the-shelf XP transceiver. That's just to communicate with all our end devices. We have 2 40-pin connectors, 26-pin 40-pin connectors for the Raspberry Pis. We use A and B. Raspberry Pis are $5, so they fail quite often, so we want redundancy. Down here we have a little power module. It's responsible for taking in the 12 volts from the solar panel and isolating all the different power rails in case something happens, a device is short or damaged, we don't affect all the different components. Kind of a functional diagram up here. We have SDI12 connectors, these are industry standard connectors. You can plug in external devices. So we use these to put a weather station into our setup. Here's how it would look like once you take the setup into the field. There's a little mini weather station up here that gives you air temperatures and precipitation information, solar radiation. So that's additional useful information that you could have in addition to all the solar moisture information in the field. Solar panel, as I mentioned earlier, electronics is housed in these enclosures and a 900 megahertz antenna for all the wireless communication. Somewhere down in here is the little 3G modem that we use from Verizon for our communication. This is the wireless end device. It's about 30 inches long. Going from right to left, these are where we connect our probes. We have 8 of these. 4 can handle digital probes. 4 will do analog probes. This is where we go put our D-size batteries. It's about 19,000 milliamp batteries, so it's pretty high capacity batteries by themselves. And then our custom electronics. Also, there's this socket here for the XP transceiver. The way it typically works is this slide is normally it's in sleep mode, and we use a relay to cut the power to minimize any residual power loss. Once we turn on the end device to make measurements, you have some sensing and transmitting and receiving. The next step is we use supercapacitors, about a couple of farads, to charge the supercapacitors from the battery. Once the capacitors are charged, we cut the battery connection off, so we can preserve that. So the rest of the operation is based on the supercapacitors. And this is a typical life cycle of that. This design has one limitation, is you cannot do very frequent measurements, because it takes time to charge the supercapacitors. So the fastest you can do is between 2 to 4 minutes. That's how fast you can do samples. But solar machine doesn't change that much. So in our application, there's no limit at the moment. I'll skip these. These are a bit hard to see, so I'll go to this part. Okay, so more practical considerations. So we have all these electronics and gadgets, so what do we do? First thing, we go outside in the field. After we identify our locations, we have to dig some holes at different depths. We have to put our sensors in the ground. A very practical consideration, both from a hydrology and an electromagnetic modeling, is the soil texture profile can vary depending on where you are. You could go from sandy, silty, clay, loamy. As you extract that, you're going to make sure you put that back in the same order, because both the soil texture, as the soil texture would change, it would change the water profile itself. So it's important to preserve that. Once you have the assembly, it's very low profile, so all the electronics are housed in these PVC pipes with a T-post. Once in a while, depending on where we are, we may have to put a fence around it. Cows like to chew on the wires, so you get some protection. This Tonzi Ranch area is next to the Ameriflux flux tower, which measures the eddy covariance and evaporation and transpiration. So having sensors around the flux tower is also very useful from other science applications. Where do we decide to deploy these, and how do we make the decision on exactly where the sensors go? Typically 3 considerations. The first and foremost is, do we have access to the land and do we have permission to the land? Some farmers like that, some farmers don't like that. Sometimes you can get permission from state or government to use the land, sometimes you don't. That's number 1. Number 2 is you also have to consider the environment you're going. What is the soil texture? What is the topography? What is the elevation? What is the vegetation? All of these at those scales that I mentioned on will affect the soil moisture distribution in terms of horizontal heterogeneity. But this is some information we have to consider when we deploy the sensors. And the last one is, where would the satellite soil moisture product end up? Once satellites go over, they do their processing, they give you a data product, there's a GPS, there's a lat long coordinate. Where is that location going to be, and is your sensor within that location? So to give you an example, these are some deterministic grids from SMAP. Once they do the radiometer processing and parameter estimation to get soil moisture, each of these little boxes, around 36 kilometers, will get one soil moisture value. If you zoom in here into the 9 kilometer, the purple ones, and 3 kilometer ones, we know exactly where the end product with SMAP would be. We were able to get land permissions to put our sensors within that. And this goes back to the representative value. We want to make sure the sensors are in the location where it satisfies what the satellite will see, and also the hydrology of the area.
Quick question. How do you make sure that when you dig a hole, put in the sensors and then put the dirt back on, that it's the way it was before you dug the hole and not affecting your measurements?
Well, there will be thousands of years soil compaction, so you just have to hammer it in. I think, where's Tianlin? Tianlin has a lot of experience in doing that, and Muhammad, so yeah, you just have to compact and make sure that. If soil normally would be a mixture of the soil particles and water. If you remove and put the soil back in, you have air gaps in there. And so the effective medium, the effective dielectric constant at the medium will be different. So you're not measuring what you're supposed to be measuring. So that's why you have to compact this out as well. There's also rocks involved, so that's all different stories. Yeah.
It's complicated.
Yes, it's complicated. And a way to mitigate that is you collect soil samples from the field, you take them to the lab, process them, and kind of help with your calibration. Okay, almost done. We have about 13 to 14 different sites throughout the US and Alaska, which is in the US, right? Sometimes you forget that, right? The top half of these, the sites, the data is available at the Oak Ridge National Lab. You can go and download that. Alaska sites were used, I'll show you an example, for air mass mission and permafrost studies. We have 2 new sites in Alamosa, Colorado, codenamed Z1, Z2. Some guys here helped us put up there. We will be processing and preparing that for Cygnus line application, something Chris was mentioning earlier. There's another one in Millbrook, it's offline. That's for the SMAP campaign next year, so we'll have that up and running. This is an address for Oak Ridge, if you're interested to get the data. It's all available. Okay, so we know soil moisture variability, different resolutions. We have a way to measure soil moisture and report it to the end user. And give 3 simple examples of how this data is used in practice. The first one is an example I made last week. 2 images of SMAP soil moisture from about August 2018 over Arizona at 36 and 9 kilometer resolution. So you can see, first of all, the 9 kilometer product captures a whole bunch of different processes, which the 36 kilometer does not. These are our in situ soil moisture sensors. Let's overlay what this map is predicting. The black dots are the 9 kilometer soil moisture estimates for pixel in this red box, and the red ones are the 36 kilometer ones. If you just look at this plot right now, you don't know which one is correct. Is map correct or is the sensors correct? Well, there's only 2 sensors here. Let's do our upscaling, do some advanced science, basically average all the sensors that we have in that area and then compare to SMAP. You get this blue line. So visually and with some very first order statistics, the matchup improves. And this is very first order approach that you try to validate the soil moisture. Once you get this, the next step is that you tell the student, okay, go figure out why there's mismatch. Mismatch could be antenna, radiometer calibration, there could be problems in the model parameterization, or it could be problems in the sensor. But once you have these two references, you can work backwards and improve the outcome. SMAP mission requirement is less than 4% volumetric. So in this case, actually, surprisingly, average of all the sensors came out of this. So that's a good idea. Another more official assessment. This is from one of our colleagues, Saab Kim at JPL. He was on the SMAP radar team, responsible for the soil moisture product. They have, throughout the world, through different collaborators, about 14 different sites, different setups, different sensor technologies that also cover different landscapes, croplands, savannas, etc. This is the SMAP time series of radar observations and the SMAP mission soil moisture estimates over this time range area. It's about 700 meters. And it looks visually and with their statistics an excellent match. So this is a way that our sensor network is helping a mission validate the product. If you look carefully here, you see the HH and VV time series. This little jump here in HH, which also corresponds to that little rain event here. It never rains in California, so it's pretty much dry. Unfortunately, the time span of the radar data we have is summertime. So in California, only one rain event. Last example is using Sourcescape data for permafrost and active layer retrieval using AirMOS. AirMOS, if you're not familiar, is a P-band SAR that was flown a couple of years ago with the goal of going and retrieving both subsurface soil moisture and attempting to retrieve permafrost. So if you look at this top figure here, there's this couple of soil temperature measurements at 5, 15, 35, and 36. There's this event here called the zero curtain. That's when for quite a while the soil temperature hovers around 0 Celsius, you would think it's frozen, but once you look at the corresponding soil dielectric or soil moisture, it does not indicate that the soil is frozen. So this active layer, which fluctuates between freeze state and thaw state, even though it's around 0 Celsius, it's not actually physically frozen. So this information helped Richard and the ERMAS team develop a 3-layer active model, a 3-layer soil model that would pair ERMAS measurements and L-band UAV soil measurements to come up with these dielectric constant and ATL estimates over Alaska. That's another way you can use Sourcescape information. Okay, I can skip that one. So, with this technology and in situ networks, there's 3 paths that are ongoing, and there are many other research tracks that we can go forward. One is what I mentioned earlier about upscaling. Now, how do you go from point measurements to a larger domain? That's a whole different science, and the simplest way, as I mentioned, is just averaging up, but there's many, many more advanced ways to do that. Another couple of projects that we're starting to work is how do you coordinate a sensor network operation between 2 sensor networks close to each other? And how do you coordinate operation with the sensor network with a UAV or another satellite information? So it's developing that infrastructure, that workflow, and translation information from one system to another. Another thing that I'm working on at MIT is, rather than going to 20-minute schedule or 30-minute schedule, how do you let the network understand the soil moisture process itself and then make a decision, should I take a measurement now or not? So it's some machine learning activities over there. And that's it. So if you have any questions, ask me or email me, and I'll be here later on to answer.